So what we know is if the distance of separation between molecules here, let's call that R on the average, how does that fall off? These interactions are proportional to what? Remember that? 325? They're proportional to 1 over R to the 6th power. So a very short range. So these molecules have to be very close to one another before they feel each other's presence. This is true except for the case of the solute electrolyte, just as a matter of interest. One over, anybody know? This is 1 over R. So these are very long range, whereas these are very short range. And we should be able to appreciate that we can always get a solution dilute enough that this fact is true. The solute-solute interactions become negligible. So that'll give us a general situation that we may be able to approach. It turns out that for electrolytes, we have to be about 10 to the minus 6 mole fraction for this to be true because of their long-range nature. But we're interested in this situation. So we should be able to define a type of dilute system, and we can call it ideal dilute when this fact is true, that is, that solute-solute interactions are negligible. And if that's the case, I should be able to say that the fugacity of some solute like this in solution, let's say we're dealing with a liquid, in the limit as x2 approaches 0 should be equal to, if that's the case, it should just be proportional to the concentration of that species in the solution. So proportional to x2, and that means it's x2 times some constant. And I'll write the constant here as a capital H with a double subscript, and I want to talk about this quite a bit, because this is Henry's law. Or dilute solutions. So it simply states that proportionality. And what it does is define Henry's constant and let's write it out here again, which requires 2 subscripts. And this identifies the solute, this identifies the solvent. Now our notation is going to be that the subscript 1 is reserved for the solvent. And subscript 2 and higher are for the solute or solutes. That's just our notation. So we would say Henry's constant for oxygen in ethanol. And that would be the situation. Well, that would give us this fugacity, and that would solve our problem for us, but how about these things? Where do we get them? Well, we have to get them out of the lab. In other words, you start measuring these solutions under very dilute conditions, and you can determine when you leave that range that then you have to get down low enough that you get a straight line slope, so that you can pull off Henry's constant. Now, general rule of thumb, I'm kind of reluctant to say this, is that you'll get Henry's law valid for non-electrolyte solutions when x2 is less than or equal to about 0.03. But take that as a rough rule of thumb, but you want to have some idea. So that defines the range of validity for Henry's law for us. So we presumably have a database for Henry's law constants that have been obtained out of laboratory measurements. And I'll show you one that I have posted for you in the files, in the figure files for today. So here are some literature values for Henry's constants for a variety of systems. So this is for the gases acetylene here, dissolved in benzene, carbon tetrachloride, chlorobenzene. This would be carbon dioxide and acetic acid, acetone, isoamyl alcohol, aniline, and the like. So you'll notice that these values are given at a rate over a range of temperatures. So if we're going to be strict about it here, then Henry's constant needs to be regarded as a function of temperature and pressure, as well as the particular system to which it applies. Now the pressure for which all of these are given is here. This is the H is in atmospheres, and the basis is 1 atmosphere. In other words, the pressure for which these apply. And that is the pressure of the particular gas plus whatever partial pressure you get out of the volatility of whatever the solvent is, usually small. So we can read these off, and what's important to recognize is that the units here are atmospheres. So all of these numbers refer to atmospheres. So the units of Henry's constant, of course, is atmospheres, the same as fugacity. I mean, it's pressure, same as fugacity. So we have a pretty extensive database here for a variety of systems. So we could go back and solve our problem now. Let's look for what system do we have here. We've got oxygen in ethanol. Should have got that before I left you. Here's oxygen, ethanol, and we're at 25C, so that's this one. So it looks like Henry's constant here is 1,730 atmospheres. So that lets me solve for X2 under these circumstances. So X2 is going to be Y2P over Henry's constant. And I've already worked this out. This is 1 minus 0.023. Pressure was 3 bar. This is 1,750. So the mole fraction that I end up with is 0.0016, well within the range for validity of Henry's law. So this particular problem then is solved. And if we have access to a database for Henry's constant, we should be able to determine solubility of a variety of gases in a variety of liquids and under different conditions. Okay, so pretty straightforward. Well, if we look at the, again, let me go back to the table of Henry's constants. We notice that for most of the situations we're given a range of temperatures. And it looks like the Henry's constant varies fairly significantly with temperature. So we should take a look at that. Now, I'm going to give you the result without proof to show you what the functional nature of this is. So this is the temperature derivative of the logarithm of Henry's constant, and that is equal to, let me write this here and then I'll talk about it. And this is derived, but I'm not gonna derive it for you, so I'm asking you to take it on faith here. This is the molar enthalpy of the hypothetical ideal gas, component 2. This is the partial molar enthalpy of 2 in 1 at, partial mole, yes, right, partial mole enthalpy of component 2 in solvent 1 at infinite dilution. And presumably that could be measured if you had a really sensitive calorimeter. So let's look at what this is. Let's just abbreviate it here. And recognize that this is a heated solution. So it's a heated solution of bringing the gas into the liquid phase. And it's the amount of heat that is either absorbed or evolved. And divided by RT squared. And it will have an order of magnitude comparable to a heat of vaporization, because I've got a gas going into a liquid.
So we're taking the oxygen and the gas in the vapor to be ideal for this derivation?
This is the definition. We're not taking it to be ideal, but this is the hypothetical enthalpy of oxygen at the temperature and pressure of the system. We get that. If it's something different than ideal, then we can calculate a departure and evaluate it. So it's that we have access to all of this. But what's important here is the magnitude. This is comparable to the heat of a phase change. In other words, fairly large, which means that the temperature dependence for the Henry's constant is expected to be fairly big. If we integrate this thing, we see it functionally looks like this. So if I were to plot up data for Henry's constant as a function of temperature in the form of plotting the log against 1 over the temperature, I would expect to get a straight line. The slope of which would be this minus heat of solution over R. So let's take a look at a special case for this, just out of the database. This is for ethylene and acetone. So ethylene and acetone, so what I'm doing is going to plot up those data in the functional form that I indicated. And the result looks like this. You couldn't get a better straight line than that. So it gives me that the log of Henry's constant here is given by this equation with an R squared value of nearly 1. And this is going to be true if you go through that database and you make those plots. So this is a typical result. Now if I have something more complicated happening when the gas dissolves in the liquid, examples of that be when carbon dioxide, for example, dissolves in water. It actually undergoes chemical reactions with water. And the same would be true if I had ammonia. So excluding those kinds of things, this is the type of result that I would expect. So that makes for a very easy interpolation or extrapolation of these results. Well, the next issue is the pressure dependence, and let me just say here before we conclude this, the pressure dependence is very weak, but I'll take a closer look at that tomorrow. And then we'll finish up this topic tomorrow, probably finish early tomorrow.